So today we're going to go over the force of friction. We need to look at what kind of things affect it, cause it, okay, those kind of things, because we're going to start running into questions that are going to involve more detail about friction as opposed to what we've been doing before, which is just, oh, here's the force of friction. Now you're going to have to figure it out from other factors in the question. All right, so obviously friction is everywhere. I don't know that it's necessarily in your notes. It's not a lot for you to write down, so I'll tell you if there's something you need to write. Okay, so friction basically, guys, is how well or how hard two surfaces stick together, or not so much stick together, but how hard it is to slide them past each other. Right? Some surfaces are very high friction, right? Like rubber on asphalt. That would be a very high friction interaction between two surfaces, right? Whereas Teflon and ice is a very low friction interaction between two surfaces, right? That's why if you've ever watched curling, okay, they have one foot that's a gripper and one foot that's a slider. I don't know if you ever noticed that, but okay, they have one foot that's covered in Teflon. And so they can slide on that foot, and the other foot is covered in rubber. Okay, it has a little bit more friction on the ice, okay, so that they can. You okay? Okay. So they can push with one foot, slide with the other. Right? An experienced curler will never step onto the ice with their slider. Okay, an inexperienced one will, and it's funny. Okay, because they step onto the ice with the foot that has very little friction, and then they go, okay, and flip over, and it looks comical. Okay, and you always step on with your gripping foot so that you don't slide. Okay. All right, so friction does have some drawbacks, obviously. Anytime there's friction, there's going to be also wear, right? And so we want to always lower the amount of friction in situations where we want surfaces sliding past each other. Okay, the most common place would be inside machinery, where we would have lubricants that would keep the metal surfaces sliding past one another, like in an engine. Okay, we have oil, okay, that keeps those metal surfaces sliding past one another in a low friction way. Okay, if your car starts to get low on oil, okay, that's bad for it. Right? If the oil light comes on in your car, don't keep driving. People do that all the time. That is the single best way to destroy your car. Okay, if that happens, then there will be friction. You will hear the grinding sound of metal on metal. Okay, then you will usually hear the snapping sound of connecting rods breaking. Okay, and things like that. Your engine will seize and your car is dead. Okay, there is no way to fix that. Okay, you need a new motor at that point. Okay, so friction can be bad if it is allowed to cause expansion of parts to the point where they can't slide past each other anymore. Okay. All right, so this situation here is similar to one that I kind of showed you earlier in the units. Okay, if I've got a person who's pushing on a desk, okay, this is not the way to do it. Why not? Which way is she pushing? Like angled, right? She's pushing downwards into the floor. Okay. The reason that's not a good way to push a desk is because by doing that, not only is gravity pushing the desk into the floor or pulling the desk into the floor, she's pushing the desk into the floor as well, increasing which force? Not just friction, the normal force, right? Because the harder we push the desk into the floor, okay, the harder the floor pushes back. So if I'm pushing at a downward angle, like it's hard to move the desk. Okay, it doesn't make any sense to try and move a desk that way. Okay, if I want to move a desk easily, what am I going to do? Yeah, lift it a little bit, right? If I lift it, there's a lot less normal force. It slides really, really easily then. Okay, all right. So the way she's doing this is not very efficient, right? Because she is increasing, okay, the normal force that's involved here. All right, so she would have her applied force horizontally, her applied force vertical, because her applied force is actually at an angle. So if we're drawing this free body diagram of the desk, okay, we would have gravity, okay, we would have her applied force, we would have, but that would be applied force vertical, her applied force horizontal, and then normal force would be really big because it would be the sum of these two, and that would affect how much friction there is. Okay, everybody with me on that? Right? If she pushes that thing straight horizontally, this force disappears. Okay, this force will decrease and be equal to gravity, and then this force will decrease. Okay, so which of these forces affects friction then? The one that reacts to gravity. Normal force. Okay, normal force is the force that affects friction. How hard the two surfaces are pushed together affects the force of friction. So the force of friction formula looks like this. It's mu times the normal force. Okay, mu is what we call the coefficient of friction. Okay, it's the coefficient of friction. Basically, it's a number that describes how sticky the two surfaces are when in contact with each other. Okay. So that number, the coefficient of friction for rubber and asphalt, would be a very large number. Okay, that number for Teflon and ice would be a very, very small number. All right, so it's just relating the two. Now, I mean, I could make lots of friction between Teflon and ice if I pushed them together hard enough. Okay, I don't know how I would exactly do that, but anyway, if I did, okay, I could make the force of friction pretty large if I made this pretty large, right? But coefficient of friction is still obviously a part of this. Okay, now the thing we need to also understand about friction is that there's two kinds. Okay, there's static friction, and then there's kinetic friction. Right? So static friction is the friction that is present when an object does not move. Okay, so static means, okay, not moving. All right, so it's the friction that's present when the object will not slide. Then kinetic friction is the friction that's there while an object is actually sliding past another surface. Okay, everybody with me on that? The formula is the same no matter what. Okay, the force of friction formula is still going to look like this. Okay, force of friction is mu times the normal force. All that changes is there's a different mu for static friction than there is for kinetic friction. Static friction is always bigger. Okay, static friction is always bigger because the coefficient of static friction between two surfaces is always bigger than the coefficient of kinetic friction. This is really important for us in the winter time. Well, anytime really driving, but okay, especially in the winter time. What is going to give you more traction? Not spinning your wheels or spinning your wheels? Not spinning your wheels. Okay, if your wheels are not spinning, the rubber is not sliding past the ice, and thus you are using static friction, and you will have more traction because traction is the force of friction. Okay, if your wheels are spinning, then you're using kinetic friction. Okay, and on ice, the problem is compounded with kinetic friction by the fact that kinetic friction produces heat, which then melts the ice, which produces a lubricating layer of water between the rubber and the ice, making the coefficient of friction even lower and resulting in you going nowhere. Okay, so the spinning of your tires on ice is less effective than not spinning your tires. Okay, same is true on a dry surface. Okay, spinning your tires on a dry surface like asphalt looks incredibly cool. Okay, get the big clouds of tire smoke, engines revving. It's very, testosterone filled. Looks cool. Okay, but it isn't effective at getting you forward, getting you moving forwards. All right, the most effective or fastest accelerating vehicles are ones that do not spin their tires. Okay? If you do not spin your tires, then more of the horsepower and torque and forces are pushing the car forward than being expended to incinerate rubber. Okay, because that's what's happening. Okay? And again, you have that problem of when the rubber slides past the asphalt, it produces heat, which burns the rubber, which produces a vulcanization or a liquid layer, okay, of rubber on the surface, causing, again, lower traction, okay, and the destruction of expensive tires. We don't want to have to be replacing them all the time. Hey, everybody with me on that? Okay, so that's the difference. Kinetic, static. I mean, that we just need to understand the difference. Calculation-wise, there's no difference. Okay, the formula is the same regardless of what type of friction we're dealing with. Okay, it's just the situation that's different. Okay, let's move on to here. So if I have, for this example here, let's have you just write down this example. So we have a static friction example. Okay, so I have this situation where the person is applying a force of 165 newtons, 30 degrees below the horizontal. Okay, the desk remains stationary. We're looking for the force of static friction acting on the desk. Okay, biggest challenge in this question is figuring out which direction friction is acting. The desk's not moving. Which way is friction acting? Because I told you the other day, friction always directly opposes the motion, and there's no motion in this question. Okay, if the table starts to move, which way is it going to go? Right, friction's going to act backwards. The table will move forwards. Right. Okay, so even though she's pushing at an angle, friction acts this way. Okay, friction can't act into or off of a surface. Okay, so in this case, friction's going to act backwards. Now here's what I have to remember about this situation. The desk's not moving. So what's the net force here? 0. Okay, so the net force vertically is 0. I'm not concerned about vertically, okay? But the net force horizontally is also 0. So how do I calculate the force of friction then if I know the net force is 0? Exactly, find the horizontal component of the applied force, okay? Friction has to be acting backwards with the same amount of force in order to stop the thing or keep the thing from moving. All right, so all I have to do is do a calculation here where I find the horizontal component of this applied force. All right, they told me it's 165 newtons, okay, and I'm looking for the adjacent side. So I'm going to go cos of 30 degrees times the hypotenuse, which was 165, and that'll give me, okay, my horizontally directed force. Okay, so went 3 again, cos of 30. Struggling. Okay, 142, so we have 3 significant figures here, 143. Okay, so we have 143 newtons, okay, worth of friction because it has to balance off the forward acting force. Okay, everybody all right with how that works? Okay, so in a static friction situation, the net force will be 0 because there'll be no acceleration, right? It can't be moving if it's static friction. Okay, so I'm going to go back to an inclined plane question here, but I'm going to alter something. Okay, this 10 kilogram mass is placed on the ramp. It does not slide down the ramp. What's the force of friction acting on the 10 kilogram block? Okay, it's a 20-degree angle, okay, 10 kilogram block. All right, box is not sliding down the ramp, so the net force is 0. Okay, so the force of friction is acting up the ramp. What's acting down the ramp? F parallel. What's the relationship between these two forces in this question? They're equal. Okay, the only way for this thing to not move is for the force of friction to be the same magnitude but opposite direction of F parallel. Okay, that way the net force would be 0. All right, so all I have to do is calculate F parallel, and I will have the force of friction. All right, so remembering the internal triangle is always normal forces there. Force of gravity is the hypotenuse. Okay, F parallels the opposite side to the angle of bank. All right, so I know that FG is going to be 98.1 newtons, and I'm going to find F parallel Okay, using trigonometry, so sine of 20 degrees times 98.1. Okay, 33.55 newtons. All right, so that's F parallel. That's down the ramp. That means the force of static friction is 30. Well, I think I only have two significant figures here. So the force of static friction will be 34 newtons up the ramp. Okay, I still have to give a direction on that. The box may not be moving, but that force is still directed up the ramp. Okay, everybody with me there? All right, next step in this question. Now I want to calculate the coefficient of friction between the box and the ramp. Okay, so I'm looking for mu. Okay, remember that the force of friction is the coefficient of friction times the normal force. Okay, and I'm looking for mu. I know what the force of friction is because I just calculated it. But I need to find mu. So that means I need normal force. Can I calculate that? Okay, here's one of the rare times where you actually have to find the other side of that inclined plane triangle. Okay, it's pretty rare, but it happens occasionally where you actually have to find the normal force side of this internal triangle. All right, it's not difficult. The normal force is the adjacent side. So instead of going sine, I go cos of 20 times 98.1 to get my normal force. All right, so we're looking at 92.18 newtons worth of normal force. So now I can calculate mu. Right, so mu will equal the force of friction divided by the normal force. All right, so that's going to be our 33.55 divided by 92.18, which means I'm going to get a decimal. Is that okay? It is. Most coefficients of friction are less than 1. And by most, I mean like 99% of them. And it's very rare to get a coefficient of friction that's greater than 1. All right, so we're getting a coefficient of friction here of 0.36. What are my units for that? Okay, what did I just divide? Nope. I just divided newtons by newtons. What happens to the newtons if I divide newtons by newtons? They cancel. The coefficient of friction has no units. None. It's a coefficient. It tells you the relationship between two forces and thus has no units. Okay? So it's one of those ones where you could forget your units because it doesn't have any. Okay? It won't hurt you in this regard. It also doesn't have direction, the scalar quantity. Okay? Coefficient of friction is how sticky the two surfaces are. That's not something that has direction. Okay, everyone following how that works? Anyone need this slide anymore? All right, so here's a slightly different thing. I'm telling you the coefficient of friction now. I want you to calculate the acceleration of this 20 kilogram box. So it's a kinetic friction question. It doesn't change the math of it. Okay, but now this box is actually sliding because they want me to calculate the acceleration of it. Okay, so the force of friction in this question, there's an applied force of 120 newtons up the ramp. Okay, that's what they're telling us at the beginning of this question. Okay, there's an applied force of 120 newtons up the ramp. I want to calculate the acceleration of the 20 kilogram box. Give you a couple minutes on that one. So first thing is we got to identify the other forces. For sure, F parallel is involved here. Okay, for sure there's F parallel. I assume the box is moving up the ramp, but I don't know that. I don't know it for sure. Okay, so what I should do is I should calculate both F parallel and the force of friction, and that will tell me whether it's moving up the ramp or not. Okay, so what I'm going to look at here is my internal triangle. So I'll have to calculate both gravity, normal force, or all three of them actually. So the force of gravity will be 196.2 newtons. No, sorry, it won't. It's not 30 degrees, it's 25. Okay, so I'm going to take 20 kilograms and multiply that. Sorry, the force of gravity is 196.2. What am I saying? It's F parallel, it'll be different. Okay, so this is going to be 196.2 newtons. Okay, and then I'm going to calculate F parallel and the normal force, okay, using my inclined plane triangle there. So the sine of 25 times 196.2 is that F parallels 82.92 newtons. All right, and then I'm going to want to also calculate the force of friction. Okay, so the force of friction is going to be mu times the normal force. All right, so I've got to calculate normal force. Okay, normal force is the adjacent side, so that'll be the cos of 25 times 196.2. So normal force is 177. They told me mu was 0.125. All right, so my force of friction is 22.23 newtons. All right, based on that, this thing is probably moving up or down the ramp? Up, okay? F parallel plus the force of friction is still less than 120, all right? So it's definitely going to be moving up the ramp, all right? So we'll have force of friction there. All right, so now that I know those forces, can I calculate the net force on the box? Yes. Okay, so net force is going to be the vector sum of all forces, so that'll be 120 minus 82.92 minus 22.23 because they're both down the ramp. All right, so we're looking at a net force of 14.86 newtons up the ramp. So now I can calculate the acceleration by taking F net and dividing it by m. So I take that answer, divide by 20. All right, so it's going to be accelerating up the ramp at 0.74 meters per second squared. Okay, what do you suppose the most common mistake on that question is? Well, not correctly anyway. Most of the time people forget about F parallel. Okay? In a question where they're told the object's being dragged up the ramp, they go force up the ramp, friction down the ramp, and they forget all about F parallel. Okay, that's the most common mistake. They do all the friction stuff right. They do all this extra calculating of normal force and all that other junk, and then they forget F parallel is involved on every single inclined plane. Okay. All right, questions on how that one worked? Okay, so frictions, I mean, yes, there's a new calculation for calculating friction, but it's not hard. You're multiplying two numbers together, okay? It's just another one of those things we have to have in our toolbox when we're, approaching a Newton's second law question. All right, so we've done one like that and like those, and we did that one. And we talked about kinetic friction, so we'll skip all that stuff because we've done that. And we've done that. All right, I want you guys to try this one here. Okay, it's like what we just did, except it's not being pulled up the ramp. It's just being placed on the ramp, and it is sliding, okay, down the ramp. So give that one a try, and then I'm going to show you the mother of all Newton's second law questions. Okay, so let's have a look at this one. So it starts out like this. It's a steep ramp, 40 degrees. Okay, so force of gravity is 196.2 newtons because we have a 20 kilogram box on there. So we need to calculate both the normal force and the force parallel because I'm going to need F normal to get the force of friction. All right, these are the only two forces on the plane, F parallel and the force of friction. So I'm going to need to calculate them both. All right, so to calculate force parallel, I'm going to take the sine of 40 degrees and multiply that by the weight, 196.2, and that'll give me 126.115. newtons. So I have 126.115 newtons down the ramp. Now I need to calculate normal force so that I can calculate the force of friction acting up the ramp in this case. So that'll mean taking the cos of 40 and multiplying that by the weight, 196.2, and that gives me 150.298. Newtons. Okay, sorry, that's F normal. Now I'm going to multiply that by mu, which was 0.185, and that will give me my force of friction. Okay, so my force of friction is 27.805 newtons, and that's up the ramp. Okay. So yeah, I had some kind of intermediate calculations that I have to do, but now I'm back to sum of all forces and F equals m times a, just like we are on every question. So let's calculate the net force here. F net in this question is F parallel plus the force of friction. So that'll be 126.115 minus 27.805. Whoop, that should have been 115. Whoops, 126.115 minus, I know I'm rounding off here, guys, 27.805. Okay, 98.31 newtons is my net force. Okay, and now I can calculate my acceleration. Just divide that by 20. All right, so the acceleration is 4.9 meters per second squared down the ramp, right? Okay, so it wouldn't be out of the question for you to get a question like that, where you had a coefficient of friction, you had to calculate normal force. Okay, that's a thorough Newton's second law question. All right, any other questions on that one? Right. So this will be the mother of all Newton's second law questions. So you want to copy it down. Okay, I will have a, let's say, 10 kilogram block on a level surface being pulled at an angle of 30 degrees, we'll say, by a force of, let's go with 70 newtons. Yeah, I think that'll work. Okay, and we know that mu for this question is 0.110, and I want to find the acceleration of the box. And that's all I give you. What should I add to my diagram right now? It's on a level surface. We'll have to figure out. Hopefully, I've picked the numbers that will work for it to slide along the surface. If it doesn't end up that way, it's flying off the surface, then I've screwed up this question. I think I picked numbers that'll make this work. Okay. It's being pulled by this kind of force, but it's possible for me to pull something at an angle. Like if I'm looking at this desk right here, okay, I can pull at an angle, right? It's not moving at an angle, it's dragging along the floor, even though the force is directed above, okay? All right, so the other forces involved in this question are obviously gravity. Okay, and for this question, that'll be 98.1 newtons, right? Friction's going to be part of this because they told me there's a coefficient of friction. Any other forces I need to be worried about? Normal force. In fact, I'm going to need that force if I'm going to calculate the force of friction. All right. Now, that's an angled force. I'd like to simplify my diagram. Okay. That force has a horizontal component and a vertical component. Agreed? All right. So I'm just going to put them on here, and I'll calculate them in a minute. So force horizontal, and I'm going to call this force vertical. Okay, that way I don't have to worry about an angled force in my question. I can just find its horizontal and vertical ones and add them to the diagram and have everything be perpendicular. Okay. All right, so let's start calculating some of these other values. Let's find F horizontal first. So we will have cos of 30 degrees, okay, times 70 newtons. So that's going to be 60.622, we'll say, newtons in a forward direction. All right, we got to find force vertical, so that'll be the sine of 30. 30 times 70 newtons. I can't believe I just did it. 35. Okay, 35 newtons. Okay, it seems like for right now that's it for right now. Right? How am I going to calculate the force of friction? I don't know what the normal force is. It's not equal to gravity because I've got another upward force. So how am I going to calculate the normal force? Tanner? I would. Why would I do that? Why will that give me the normal force? Exactly. The box is going to stay on the table, meaning the net force vertically is 0. Right? The box is not moving vertically. It's not accelerating vertically. It's being dragged along the table. Right? That means that my normal force and my force vertical have to add up to 98.1. Right? So I need to calculate my normal force by simply taking 98.1 and subtracting 35. Okay, my normal force is 63.1 newtons. All right, so that's kind of the first intuitive step to that question, is realizing, okay, it's not moving vertically, so all the vertical forces, the 3 of them, add up to 0. That helps me calculate the one I didn't know. All right, now that I know normal force, can I calculate friction? All right, so friction is going to be mu times the normal force. And they told me what mu was in the question, 0.110 times 63.1. All right, so 6.941 newtons worth of friction. All right, I got a lot of crap on this diagram. Okay, do I need much of it? Not anymore. Okay, I had to calculate most of those forces so I could calculate the forces that were important. The only 2 forces that are now important for an object sliding along a table are those 2. Okay, once I've calculated the other forces, okay, this is what it breaks down to. It's sliding along a table, forwards with 60, backwards with 6.941. Okay, I can calculate the net force. All those other ones added up to 0. They didn't matter. Okay, so now I can calculate F net by simply going 60.622 and subtracting friction, okay, 6.941. All right, so we got a net force of 53.680 newtons forwards, right, which means that my acceleration will be 5.4 meters per second squared. Okay. So there's several intuitive leaps and a fair amount of intermediate calculating in a question like that, but it still came down to sum of all forces and F equals m times a. Right. There has never been a unit exam without that question on it. That most of you are not making a note of that. All right, we're going to leave it at that. Okay. Remember that your Newton labs are due on the 25th. Okay, so we did that yesterday. Hopefully you all have your data, graphs are built, okay, getting to work on the analysis and such. Okay, so know that that's coming up. On Monday, okay, guys, listen up. Okay, you got plenty of time to pack up here. Okay, on Monday, we're going to be kind of doing some more complex Newton's second law stuff, and then I'm hoping I can talk about Newton's third law later in the period on Monday. Tuesday, we'll have a quiz, and we'll see how that goes. If it goes well, because it's going to be tougher questions on that one, okay, then we may say we're good with Newton's second law and move on. Right, but we'll have to see how that goes. Right. There will be an assignment like your vector assignment on Newton's second law. That'll be next week as well.